All right, good afternoon, ladies and gentlemen. So this particular video is going to cover the first half of kind of introducing just another topic. We're still talking about rotational motion, and we're just adding a new thing to our kind of repertoire of knowledge for rotational motion. But before we can do that, the first thing we're going to do is we're going to review what we've already talked about so far with rotational motion. So the first thing we've talked about is the idea that all the linear topics we've talked about so far seem to have rotational versions, and they still follow the same rules. They're just kind of tweaked a little bit to adjust for the fact things are going in circles now instead of going in a straight line. All right. Now, going through the various topics we've discussed already, we kind of have rotational versions for at least 5 things right now. So the first thing we do is a rotational version of force. All right. And actually what I want you to do is, this is kind of your warm-up. Pause the video, fill in these 5 things. All right, just kind of type in the words. You don't need to try and do the symbols unless you really want to. All right, so just pause the video, do that as your warm-up. When you're done, unpause it. All right, so for your warm-up, we're just kind of labeling these things. So the first thing we talk about is the rotational version of force. All right, remember that is a torque. And that is basically a force that is applied some distance away from the turning point, and it's going to cause something to rotate. All right. The next thing is the rotational version of mass. Now that's that weird thing we discussed in the last video called the moment of inertia. And remember, that is basically a measurement of an object's mass and how far away all the mass is from the axis of rotation. All right. Now, right now, going down the line, rotational version of linear displacement. Oh my gosh, congratulations. It's angular displacement. Wow, that's pretty wild. All right. And of course, going through the other ones, linear velocity is angular velocity, which is represented by that little omega, that curly W. Linear acceleration, angular acceleration, which is represented by alpha, or that little fish symbol. All right. But in all these cases, ladies and gentlemen, we're just getting used to the idea that we now have a bunch of different linear topics we talked about before, and we now know their rotational versions as well. All right. Now, we know that all the rules that have applied for linear motion seem to apply for rotational motion as well. So that leads nicely into our next question. It's pretty simple. All I want to know is, how can I store energy in a wheel? All right. And it can be as simple as literally make a bicycle wheel that I can just hold on to and you know, I just want to know how I can store energy in a wheel. So take 10 seconds, just kind of think about it. All right. Now, of course, if you look right beneath this, you might already start to think we're getting an idea here. The easiest way I can actually store energy in a wheel is I can literally rotate it. I can give that wheel rotational energy. And what happens is, actually, that is a form of kinetic energy, because that is motion. All right, which leads nicely into our next topic, which is rotational kinetic energy. All right. Now, rotational kinetic energy is pretty much exactly what it sounds like. And what it is that objects that are spinning or rotating, doesn't really matter which, objects that are spinning, rotating, have some energy. All right, because clearly they're moving, and we've discussed before that any sort of object that is moving has kinetic energy. Now, of course, we talked about this when we talked about kinetic energy originally. I was throwing things at people. It was great times. And we were talking about how much it hurt. In this case, you can kind of think about it as, if I took that wheel that was spinning and I basically pushed it on you, you talk about the pain that you were feeling as it kind of, scraped against your arm. So it's the same idea. So objects that are spinning or rotating are clearly moving, and therefore have kinetic energy. In this case, rotational kinetic energy. All right. Now, with rotational kinetic energy, we look at it the exact same way that we did with traditional linear kinetic energy. We just have to change the formula slightly to adjust for that. So remember, for linear kinetic energy, linear KE, we know that it's 1/2 times the mass times the velocity of the object squared. All right. Well, rotational kinetic energy is slightly different in that we just kind of translate all the linear things into their rotational versions. All right. So it's still 1/2. Fractions are still fractions. Instead of using mass, though, you now use the moment of inertia of that object that is rotating. All right. And then, instead of using linear velocity, you're going to use angular velocity, which is curly W, but it's a pain in the butt to kind of figure that out, so I'm just going to use a W instead. Okay? But what we can see with rotational kinetic energy is, in order to increase it, there's honestly two things you can do. So to increase it, you can either make the object spin faster, which makes sense. If you spin it faster, it's probably got more energy in it. It's moving faster. Or you can increase the moment of inertia. All right. Now what that means is you can adjust where the mass is located, move it farther away from the turning point. That can give it more energy. All right. It's the same idea. If for normal kinetic energy, we talked about linear kinetic energy. If I have two objects going the same velocity, but one is much bigger than the other, much more massive, it has a lot more kinetic energy. All right. So right there, we're just thinking about the idea, ladies and gentlemen, how I can affect my rotational kinetic energy, or how it can affect me. So make objects spin faster, or increase moment of inertia. All right. Now, of course, if we have rotational kinetic energy, it means that we can actually also take work and we can move it into the rotational frame of mind. All right. Now, unfortunately, rotational work does not have some fun, fancy name. It's just referred to as rotational work. So, right here, where this little fill in the blank is, if we have rotational kinetic energy, it means we can do rotational work to change the energy of the system. All right. Now, remember, traditional work, we're going to call it linear work for now, is just equal to the force times displacement. So remember, that's delta x. We're just going to call it x times cosine of the angle. All right. Well, rotational work is slightly different. And what it is basically we kind of change it accordingly. So what it is now is rotational work is going to be the torque times the angular displacement. All right. And it's kind of strange at first because you might ask, where did that cosine of theta go? It disappears. All right. It doesn't actually matter anymore. All that matters is the net torque acting on it and the delta theta, the angular displacement. All right. But strangely enough, both those things still produce a change in energy in joules. All right. So even though this is a weird torque angular displacement thing, it's still producing energy in joules. All right. Now, we use this to kind of lead into talking about what happens when you start to include rotational kinetic energy. So a long time ago, we talked about the idea of a weird little system where you just had two masses hanging over a pulley and you let it go. All right. And we like to try and make sure the masses were different size so that once I let go, one would start moving and pulling the other one with it. All right. Now I've done just that. I've set up a situation where I have a pulley. I have a large 3m mass object hanging in the air. It's at a height of h over the ground. And then I have a small, just m mass sitting on the ground. So it's a height of 0. Now, right now the pulley is massless. And we're going to talk about in a second why that's important. But the first thing I want you to do is I actually want you to write out the law of conservation of energy for this system. All right. Now, what I'm going to do is I'm going to let the system go. And of course, the large mass is going to start moving. So what I want you to do is basically write out the law of conservation of energy for those masses, where the beginning, the initial part, is when the masses, I have not let them go yet. So the 3m is sitting in the air, the m is on the ground. And then I want you to write it for when, the very end of this, when the 3m reaches the ground, literally at the instant it reaches the ground, the m1 is now in the air and they are moving. All right. So take about as much time as you need, and I want you to just write out the law of conservation of energy real quick, and then we'll talk about it. All right. So writing this out, starting from the beginning, at the initial point, nothing's moving yet. All right, which means the only types of energy we have are gravitational potential. Now, looking at it, if we look at the two objects, the only thing that actually has potential energy is the 3m mass object. The other one's on the ground, height of 0, it actually functionally has no potential energy. So in the initial part, we only have U, and I apologize that I'm not going to make it subscript, UGI for the 3 mass, or the 3m one. Okay, that's all we got. That means the total energy of the system is just equal to the potential energy of that big block. Now, afterwards, I let them go. They start to move, which means now both blocks start to gain kinetic energy. And remember, they are moving at the same velocity because they are connected. That means at the end of all this, we have a couple things going on. I know that the 3m mass has kinetic energy. I also know that the mass m1 also has kinetic energy. But I also know, looking at this, that the small mass has now been pulled into the air, so it actually has gained potential energy. So at the end of all this, it actually has UGF. It has potential energy as well. All right. So now what we see is that, look, writing at the law of conservation of energy, and I'm not worried right now about writing any formulas. Writing all that out, we see that it starts with just potential. At the end of all this, it has kinetic and potential. Nothing is rotating, so we don't have to worry about anything like that. And it's all set up exactly the way we thought it should be. All right? And that's something, when we've talked about this before, it's linear motion. Now, here's where it gets interesting. In reality, we always like to make the assumption in this class, we like to say that the pulley is massless. And it didn't really make much sense why we would say that before, but it will now. Because in reality, pulleys are not massless, which means that it takes some energy to have them start to rotate. All right? Now, because of this, our system looks slightly different. So what I want you to do is, I actually want you to answer this question without doing any calculations whatsoever. I want you to explain why the masses will actually move slower than the predicted situation above. Okay? And remember, the pulley now has mass. So think about what's going on here. Think about your energy transformations. Once you think you got an answer, come back. We'll talk about it. All right? Hopefully you had a chance to think about it and kind of look at energy and what's going on here. The reason that the masses are now moving slower is because there are now 3 objects in the system that have mass. All right? So the potential energy, the starting potential energy now is being divvied up between 3 things at the end of all this. So the starting potential energy is now going into the kinetic energies of both blocks and the kinetic rotational energy of the pulley, which means there's not as much linear velocity there's not as much linear kinetic energy that can go into the blocks. So they have to move a bit slower. So we can just say the starting potential energy is now divided 3 moving objects. Thus the kinetic energy of boxes, hanging blocks is less. All right. Now we can rewrite that as well in a handy little equation to help us out here, just to kind of visualize it. So what would happen now is that basically this would look exactly the same if we wrote our formula. So if we write out my law of conservation of energy formula, what it would look like, and I'm going to copy this one because we're going to really modify it, is we start with technically 2 things in the air. All right. So we'd start like this. We'd have the gravitational potential energy of the big mass plus the gravitational potential energy of the pulley. But what we can do is a little trick, just make our lives a little bit easier. If the gravitational potential energy of an object doesn't change, you don't need to include it in your law of conservation of energy. So I'm not going to include that. So we start with the same potential we did before. We end with the same objects having kinetic energy. And of course, the small block now has potential. But we now have to include the rotational energy. So I'm just going to put KROT for rotation of the pulley. And now we can see that there are now 4 different energy terms that the starting potential energy has to kind of be divided between, as opposed to the original 3. So because of that, the linear velocity of those 2 hanging blocks is actually going to be a bit slower. All right? It's just like if we were drawing our energy bar chart, we'd have maybe 4 blocks of energy starting with this, but now those 4 blocks have to be distributed between 4 different things as opposed to the original 3. All right? So this is where we're going to see how linear kinetic energy and rotational kinetic energy work together. We're going to see that a lot of things that we thought should be moving faster in this class were actually moving slower because rotational kinetic energy was in play. All right? So with that being said, ladies and gentlemen, that is where we're going to stop for the first half of this video. The second half is a practice problem that goes into detail about how linear and rotational energy kind of work together. So with that being said, you can head to the second video, and I'll see you there.